Pure silica glass is rather difficult to work with, so precision manufacturing and processing techniques were developed to make high-quality optical fiber based on the vapor deposition process. With the inside method, ultra-pure silica, germanium, or other elements are vaporized and applied to the inside of a silica tube heated by a hydrogen flame or a microwave plasma. Each pass of the heat source fuses a small amount of raw material to the inside of the tube as a thin layer of glass. The composition of the vapor is designed to create layers of glass with a refractive index usually higher than the silica tube. These layers will form the fiber's core, while the tube becomes the cladding. When enough core material has been built up, the tube is strongly heated to collapse it into a solid rod called a preform. The preform may have been constructed as a primary preform for use in a subsequent overclad operation to make the preform larger, or it could be a final preform, which is a scale model of the finished fiber, only much shorter and thicker. In either event, the finished preform is then installed in a drawing tower, where it is melted and stretched into an optical fiber many kilometers in length. The inside vapor deposition process we just described has been implemented in two forms. The first is the Modified Chemical Vapor Deposition Process, or MCVD, which uses an oxygen-hydrogen torch as a heat source. The second form is the Plasma-Activated Chemical Vapor Deposition Process, which uses a plasma. In addition to these inside processes, there are two outside deposition processes, the Outside Vapor Deposition Process, or OVD, and the Vapor Axial Deposition Process, or VAD. In the outside vapor deposition process, vaporized raw materials are applied to a rotating mandrel, first to form the core, then the cladding, to make a soot preform. The mandrel is then withdrawn, and the soot preform strongly heated to collapse the center hole and form a rod of clear glass. The preform can then be drawn into a continuous fiber strand. With the vapor phase axial deposition process, a silica glass starting rod is rotated with its end initially in one or more hydrogen flames. Vaporized components flow through the torches and are deposited on the end of the rotating rod. As the rod moves upward, sooty particles are deposited, forming a soot preform. A consolidation furnace is then used to fuse the particles into a solid transparent glass preform, which is then overclad with more glass and ultimately drawn into fiber. Over the years, improvements in manufacturing processes have resulted in fiber with very tight tolerances in core, cladding, and coating geometry. This has been instrumental in the emergence of advanced optical components such as circulators, add-drop multiplexers, couplers, switches, and polarization control products, just to name a few. Consistent dimensions of core and cladding make it possible to rely on outside cladding diameters to align fibers. This has led to the development of fiber ribbons that can be mass-spliced. Ribbon fiber consists of up to 24 parallel fibers held together in a planar array with an acrylic material. Consistent fiber size is also critical when using fixed V-groove alignment splicing or when assembling connectors. These devices rely on the outer cladding diameter for accurate alignment. A difference of only a few microns in cladding diameters can result in a splice with unacceptable losses due to severe core misalignment. Core concentricity refers to how well the fiber core is centered in the cladding. Here, too, inconsistent tolerances will yield poor quality splices and connections. This is especially true when using fixed V-groove alignment in mass splicing applications where fibers are not adjusted individually. Concentricity values are established during the deposition process to less than 0.5 microns. Fiber curl describes the amount of curvature that exists along a given length of fiber. Concern with fiber curl was not an issue until the advent of mass splicing techniques used with ribbon fiber. It is directly related to the manufacturing process and consistency of coatings, glass geometry, and draw characteristics. With the continuing trend of higher densities and miniaturization in optical systems and subassemblies, ribbon fiber can be used to form optical flex circuits, similar in nature to the flexible mylar circuit boards used in electronic systems. Optical flex circuits offer a very small bend radius and are designed for applications where density and flexibility are critical design factors.